Okay, welcome to session 22, part D. Okay, um, in this part, so last part we just talked about fractional reserve banking. Okay, now we also talked about when a goldsmith had fractional reserve banking. So Goldsmith A only had to keep 60% of his gold at his shop and then he lent out the other 40%. How that increased the money supply when he does this. Okay. It turns out when a bank only has to keep a fraction of its money in reserve in its vaults, then it increases the money supply and it increases by a specific amount. We call that amount the expansion multiplier. So what it means is and I'll talk about this in a minute. The expansion multiplier is 1 over the reserve requirement. Okay, so if the reserve requirement is 10%, the expansion multiplier is 1 over 10%, that's 10. Okay, so that means if the expansion multiplier is only 10%, that when banks continue to lend, they increase the money supply by a factor of 10. Okay, I'll go through an example to show that. So if the government starts off with $20 trillion total dollars in gold and paper money and so on, those go to banks. The banks only have to keep 10% of their deposits in the reserve. Everyone uses the banking system. It means that the money supply will expand by a factor of 10, that the total money supply will be 10 times that 20 trillion, 200 trillion. Okay. Okay. I'm going to get to that in a moment. Okay. Before I do that, I want to go over a math concept, though. Okay. Now, to understand this math concept, the proof, and to understand it fully, you need to take a course in what's called real analysis. And this is a course, it's pretty involved. It's usually the course you take after you've had a year of calculus, where you go back to the calculus you've done and actually do the proofs of it. Okay, we won't do that. Okay, instead I'm going to take one little concept from real analysis and try to explain it in layperson's terms. And in fact, I'm going to explain it in terms that you may have already heard about it, maybe as early when you're in 5th grade or so. Okay, and this idea starts off with the notion, hopefully you've heard about it before, where you have a wall and you have a frog that is 2 meters from the wall. Okay, so this is a distance of 2 meters. And what's going to happen is the frog is going to start taking jumps toward the wall. Each jump, the frog jumps half the distance that remains to the wall. Okay, so what that means is his first jump, he's 2 meters away, his first jump is going to be 1 meter. Okay, so now he's at that point, he's 1 meter away from the wall, he's jumped 1 meter away. He's got to jump half of what he is away from the wall, and that means a half meter. So he jumps half meter. So he's jumped 1.5 meters. He's a half meter away from the wall. He's going to jump half again. He's going to jump half that distance, which means the next jump, he's going to jump here, and it's going to be a 1/4 meter. And he keeps on doing that. Okay. Now, you may be familiar with this, maybe from 5th grade or so. And the key point is that the frog keeps on jumping, but he never actually touches the wall. He can get arbitrarily close to the wall. So you can give me some distance, no matter how tiny you make it, say 1 millimeter. And I can calculate how many jumps it would take for him to get within 1 millimeter of the wall. Okay, but you can't name a distance of 0. You can't actually touch the wall. Okay, the idea is that he will jump an infinite number of times, but he will never actually get to the wall. Okay, the key point is here we have a situation like this where the frog jumps a fraction of the distance that he jumped formerly. Okay, I'll explain this a little more fully in a second. If he keeps doing this, he can jump an infinite number of times, but he will only go a finite distance. Okay, so in this example, the frog jumped an infinite number of times, but he only went 2 meters. In fact, actually just a teeny bit less than 2 meters. Okay, so that's the key point. Okay, that's at least the warm-up point. Okay, now I want to change this. Okay, and I want you to think about a frog. Instead of it being 2 meters away, let's make it be 10 meters away. And if I remember my metric system right, that is 1,000 centimeters. Okay. Now, so the frog is 1,000 centimeters away. Now, instead of jumping halfway toward the wall, each jump, he jumps 1/10 of the distance to the wall. Okay. So that means he jumps 100 centimeters. Okay. That means he's now 900 centimeters away. He's going to jump 1/10 of that, the next jump. So that means 90 centimeters. Okay. 1,000 minus 100 minus 90 is 810. Okay. So now the next jump, he's going to jump 1/10 of that. So he will jump, the next jump will be 81 centimeters. Okay. Now, the key is, now one thing I want you to see, and I hope you'll agree with me. So every time he's jumping 1/10 of the way toward the wall, as you can see, same thing's going to happen. He's going to do an infinite number of jumps, but he's only going to go a finite distance. Okay, he will only go a total of 10 meters. Okay. Another way of looking at this is just to say, look, his first jump was 100 centimeters. Every jump after that is 9/10 of the former jump. Okay, 100 centimeters was the first jump. 9/10 of that was the second. 9/10 of 90 is 81. The next one. Okay. And if I didn't tell you the wall was 10 meters away, it turns out we can use this math. There are some math tricks that will say you just keep on adding those up, and it turns out the total distance is going to be, so he jumps 1/10 of the times the first jump. The total distance times his first jump is going to be 1 over that 0.1, and that equals 10. So he's going to jump 10 times the amount of his first jump. Okay, here, don't worry if you don't understand it. Trust me, it worked when we had the wall up. There's some math techniques that to prove this, you won't learn those until after you've had a year of calculus. So don't worry about the details, but just trust me that he will jump 10 times this total distance. 10 times 100, it's 1,000. If he keeps doing that, jumping 9/10. It turns out the formula is 1 over 1 minus 0.9, and that equals 10. Okay, so trust me, he will jump 10 times that first jump, 1,000 centimeters. Okay, all right. So that is a little bit of math for some warm up, the frog jumping problem. Now let's talk about fractional reserve banking. Okay. Here is how this works. Okay, so suppose that you deposit $1,000, say in gold, to a bank. If you like, just think of it as that goldsmith. If it's easier to think of it instead of as a bank. So you've actually, suppose you have $1,000 in coins, okay? In the old days when, we had gold coins. You give that to the bank, okay? The bank has So the bank gives you that back out in checking deposit. You write checks on that. Those checks are like money. Or think of it's like the goldsmith. The goldsmith has given you IOU pieces of paper. Okay, those pieces of paper are just like money. Okay, so that means there's now $1,000 in money. Okay, so money supply equals $1,000. Okay. Okay, now let's suppose that bank or that goldsmith, that bank lends 900 to another bank. Okay. That second bank can do what it wants. Notice we use the 10% reserve requirement. So the first bank keeps 10% of that money in its vaults, okay, lends out the other 900, okay. With that 900, that bank can use that to buy stuff, to invest, or can lend it to other people. It can do it at once, and that 900, it can write notes on that, say checking notes, okay? With that 900, it can create $900 worth of additional paper money. That means is that the money supply is now 1,000 plus this 900. It's like the goldsmith. Before he had 100 ounces of gold, he had 100 ounces, 100 1-ounce notes. He lent out, what do we say, 40, and he created 40 more. So now the money supply and these 1-ounce IOU notes are now 140. Okay, same thing. Now it's 1,900. Okay. That 900, let's say that 900 goes to other banks. Okay. People receive that. They buy and sell, use that money to buy and sell. The sellers get the money. They deposit that money in other banks. Okay. That 900 goes to other banks equals okay. They keep the second bank has $900 worth of deposits. Okay, that bank has 900 in deposits. Okay, it can use 9/10 of that for transactions. Okay, that is, it can lend it, it can create notes, it can buy stuff with it, it can. So that 9/10 of that can go for other transactions, and so that money is 9/10 of 900, which is 810. Okay. That adds to the money supply. Okay. That money is eventually deposited at other banks. Those banks can use 9/10 of it for transactions. And that adds more money to the money supply. So plus 0.9 times 810. Okay. So here's what we have, and this can go on an infinite number of times. Okay. And notice this is just like the frog jumping, okay? The frog first jumps 1,000 centimeters. What did I say? I did that problem wrong. I probably should have meant it 1,000 millimeters. It jumps 1 meter, okay? Um, uh, Whatever the case, he jumps 1,000. Okay, actually, I said 100 centimeters. Say it was 1,000 millimeters. Okay, he jumps 1,000, and then 9/10 of that, 900 millimeters, the next jump. Then 9/10 of that, the next jump, 810. Then 9/10 of that, 0.9 times 810, the next jump, and he keeps on doing that, and then the final jump, how far a distance, even though he's going to make an infinite number of jumps, he'll only go a finite distance. And the total distance is going to be, the reserve factor is over 1 minus 1 over 0.9. The way the jumps decrease, and that equals 1 over 0.1. That 0.1 turns out it's the same thing as the reserve requirement. And this equals the expansion factor. So you multiply, and that equals 10. Multiply 10 times the original jump, 10 times, or this time, or the original amount of money, 1,000, and you get $10,000. Okay. So what that means is the total supply of money, after you have an infinite number of instances like this, okay, you keep on expanding the money supply by 9/10 of that former amount, you do it an infinite number of times, you'll only expand it by a finite amount, and it turns out it will be 10 times, the new total money will be 10 times the original amount. Okay, so that probably wasn't as clear, probably as the book was. Hopefully I've at least added something to your understanding about this. But the key is, look in the book. So the key is you take the fractional reserve requirement, you take 1 over that amount, and that equals the expansion factor. Okay, and sorry, my handwriting is probably not that good. So you take 1 over the fractional reserve requirement. Okay, that number equals the expansion factor. Take the expansion factor, multiply it by the original amount of money. Okay, that's how much is the total money supply. And so the idea is that if you start off with a total amount of currency and coins, and that is some amount, the fractional reserve requirement is 10%, take 1 over that amount, the expansion factor is 10, so 10 times whatever the currency and coins were, that's the new total money supply. On the other hand, okay, if the fractional reserve requirement, say it were 20%, okay, let's say that the government has a total of $1 trillion in currency and coins, okay. Fractional reserve requirement is 10%. That means the total money supply will be 10 times that, 10 trillion. Okay. What if instead the fractional reserve requirement were 20%? Okay. So now, let me use a red marker. So fractional reserve requirement equals 0.2, 20%. 1 over that is now 5. So that means the expansion factor now equals 5. What's the total money supply? Now it's only 5 trillion. Okay, so you can see when all of a sudden the reserve requirement goes up, the total money supply will go down. Okay, and it goes down or up, or actually the total money supply just equals the original amount of currency times that expansion fraction. Okay. Okay, so I will end there. That's part D. See you in part E.